The research paper investigates topological phase transitions in three-dimensional multi-component lattice Abelian-Higgs models, characterized by a global SU(n) symmetry. These models consist of an n-component scalar field minimally coupled with a noncompact abelian gauge field. The phase diagram exhibits three phases: a high-temperature Coulomb phase, and two low-temperature molecular and Higgs phases, both featuring spontaneous breaking of the SU(n) symmetry. The molecular Higgs and Coulomb-Higgs transitions are topological transitions, separating phases with gapless gauge modes and confined charges from phases with gapped gauge modes and deconfined charged excitations. These transitions cannot be described by effective Landau-Ginzburg-Wilson theories due to the active role of the gauge modes. The study reveals that the molecular Higgs and Coulomb-Higgs transitions belong to different charged universality classes. The Coulomb-Higgs transitions are associated with the independent charged fixed point of the renormalization-group flow of the 3D Abelian-Higgs field theory. In contrast, the universality class of the molecular Higgs transitions is independent of n and coincides with that controlling the continuous transitions of the one-component law model. The gauge critical behavior corresponds to that observed in the 3D inverted XY model, and the correlations of an extended charged gauge-invariant operator exhibit an independent critical universal behavior. Numerical results for n equals 1, 2, 4, 10, 25 support this scenario. However, the molecular Higgs critical behavior does not appear to have an interpretation in terms of the RG flow of the AHFT, as determined perturbatively close to 4 dimensions or with standard Largan methods. The study aims to understand emergent collective phenomena in condensed matter physics, such as transitions in superconductors, quantum SU(n), antiferromagnets, and unconventional quantum transitions between the Neal and valence bond solid phases in two-dimensional antiferromagnetic SU(2) quantum systems. The kappa-J phase diagram of the n-component lattice Abelian-Higgs law model exhibits distinct phases for different values of n for n equals 1. The Coulomb and Higgs phases are characterized by confinement and deconfinement of charged gauge-invariant excitations, respectively. In contrast, for n is greater than or equal to 2, the scalar field is disordered in the Coulomb phase, while the molecular and Higgs phases exhibit long-ranged gauge correlations and spontaneous breaking of the global SU(n) symmetry. Multi-component law models undergo charged deconfinement transitions, particularly along the MH transition line between the molecular and Higgs phases. These transitions are driven by a qualitative change in gauge correlations, without a local gauge-invariant order parameter. To investigate the critical behavior of these transitions, finite-size scaling analyses of Monte Carlo data are performed for n equals 1, 2, 4, 10, and 25. The results indicate that the charged topological transitions are continuous and belong to the same universality class as the CH transitions in the one-component law model, which is related to the inverted XY model. The 3D law model is defined, featuring n-component complex vectors and noncompact gauge variables, with the scalar field coupling J rescaled by a factor of n to ensure a finite limit as n approaches infinity. The Hamiltonian and partition function are also defined for the 3D noncompact lattice Abelian-Higgs theory. The general features of the phase diagram and transition lines are summarized, with numerical results revealing that the MH transition line is continuous and exhibits universal behavior. The results provide insights into the critical behavior of multi-component law models, which have implications for our understanding of gauge theories and phase transitions in statistical mechanics. Key numerical results include the critical exponents and correlation lengths obtained from finite-size scaling analyses, which demonstrate that the charged topological transitions are continuous and belong to the same universality class as the CH transitions. These findings provide strong evidence for the existence of a novel universality class, which is distinct from the traditional 3D XY model. The paper also discusses the implications of the results, including the relationship between the MH transition line and the CH transitions in the one-component law model. The limitations of the study and future directions are also discussed, highlighting the need for further investigations into the properties of multi-component law models. The 3D lattice Abelian-Higgs model is defined with a global SU(n) symmetry and local abelian gauge invariance. However, the partition function diverges due to zero modes related to gauge invariance, even with maximal gauge fixing and periodic boundary conditions. To overcome this issue, C*operator boundary conditions are adopted, which preserve local gauge invariance and softly break the global SU(N) symmetry to oxygen mononitride. The Lorenz gauge fixing is used to compute gauge and scalar correlation functions, breaking the invariance of the model under gauge transformations. The lattice Lorenz gauge is convenient, as it only exhibits zero-mode singularities in the infinite volume limit. Alternatively, for n equals 1, a unitary gauge fixing can be used, fixing Zx equals 1 and leading to a soft version of the ICSI gauge model. The kappa J phase diagram of the 3D law models exhibits distinct features for n equals 1 and n is greater than or equal to 2, due to the possibility of spontaneous breaking of the global SU(N) symmetry for n is greater than or equal to 2. For n equals 1, two phases are present: a Coulomb phase with gapless gauge correlators and a Higgs phase with gapped gauge correlators. These phases are separated by a transition line connecting the transition points in the J right pointing arrow infinity sign and kappa right pointing arrow infinity sign limits. In the J right pointing arrow infinity sign limit, the law model becomes equivalent to the ICSI model, and in the kappa right pointing arrow infinity sign limit, it becomes equivalent to the standard O(2) vector spin model. The transition points in these limits are located at kappa c, J right pointing arrow infinity sign, equals 0.076051, 2, and JC, kappa right pointing arrow infinity sign, equals 0.22708234, 9, respectively. The multi-component lattice Abelian-Higgs law model, characterized by an additional SU(N) global symmetry, exhibits a complex phase diagram comprising three distinct phases: Coulomb, C, molecular, M, and Higgs, H. These phases are separated by three different transition lines Cm, carbon monohydride, and Mh. The Cm and Ch transitions have been thoroughly investigated. The Cm transitions belong to the same universality class as the 3D-CPN1 model, with a stable uncharged fixed point. For n equals 2, these transitions can be continuous in the O(3) vector universality class, while for n greater than 3, they are generally first-order transitions. The Ch transitions are associated with a stable charged fixed point of the Rg flow of the Abelian-Higgs field theory, corresponding to the formal continuum limit of the law model. Continuous Ch transitions occur for n greater than n* operator, with n equals 7, 2. Critical exponents depend on n, consistent with Largan field theory predictions. However, the Mh transitions have not been extensively analyzed. They separate two ordered phases, both characterized by the condensation of the gauge-invariant bilinear Cobb. These transitions are related to qualitative changes in gauge correlations without a local gauge-invariant order parameter, similar to the Ch transitions in the one-component law model. The Mh transitions are continuous for sufficiently large but finite values of J and controlled by another charged fixed point, different from the AHFT fixed point controlling the Ch transitions. This Mh fixed point is the same as that controlling the J right pointing arrow infinity ICSI transition and the continuous Ch transitions in the n equals 1 law model. The existence of the Mh transition line for n is greater than or equal to 2 can be inferred from the presence of two low-temperature phases distinguished by the nature of the gauge correlations. This is suggested by the ICSI transition in the J right pointing arrow infinity limit. A natural hypothesis is that the Mh transition line is continuous and controlled by the same fixed point as the J right pointing arrow infinity ICSI transition. This hypothesis is supported by the observation of a single, continuous, transition in the n equals 1 model and the presence of a continuous transition in the J right pointing arrow infinity limit for any n. The multi-component lattice Abelian-Higgs law model is investigated, with a focus on the critical behavior of the magnetic to Higgs Mh transition line and its relation to the ICSI transition point. For n is greater than or equal to 2, The MH transitions may exhibit n-dependent critical behavior due to the presence of massless Goldstone bosons, potentially belonging to a different universality class than the ICSI transition. Alternatively, residual scalar fluctuations may decouple from topological gauge field critical modes, resulting in the same critical behavior as the ICSI transition. In the Largan limit, the phase diagram simplifies, and the MH line is expected to be a straight line corresponding to kappa equals kappa c, ICSI. The MH line is argued to be independent of J, similar to the J right pointing arrow infinity limit, but with the important difference that the number of components of the scalar field changes. By considering magnetized boundary conditions, the scalar Hamiltonian converges to a single component quantity, implying the equivalence of the two limits. The critical behavior along the CH line is predicted to be independent of the gauge fields, with the AHFT predicting a straight line with J equals JC. Infinity equals 0.252731. Where JC, infinity is the value of J where the O(n) transition occurs. Numerical simulations suggest that the Largan transitions are of first order for n is greater than or equal to 3, and become stronger with increasing n. The authors conjecture that the CM transition line corresponds to the line J equals JC, infinity for all values of kappa. Gauge-invariant energy cumulants, intensive quantities related to the energy central moments, are highlighted as a suitable set of observables to characterize the critical behavior of the MH transitions. These observables are essential for studying the law model's critical behavior. Gauge field correlations in the Lorenz gauge are a crucial aspect of understanding gauge-invariant correlators. To investigate these correlations, gauge-dependent correlation functions for the Fourier transformed field A micro, P, and the gauge field susceptibility chi-A are defined. These quantities are related to gauge-invariant correlators, such as the plaquette susceptibility chi-F, through equations 23 and 24. Specifically, the second moment correlation length of the gauge field, xi-A, is defined and linked to particular correlations of the plaquette operator in equation 18. The analysis of gauge field correlations in the Lorenz gauge provides valuable insights into gauge-invariant correlators. The paper demonstrates how gauge-dependent quantities can be used to understand gauge-invariant correlators and their critical behavior. Furthermore, scalar field correlations are examined by defining scalar field observables Ez, P, and Egz, P, as well as the susceptibility chi-Z and length scale xi-Z. These quantities are essential for understanding the behavior of scalar fields within the system. The binder cumulant ooze is introduced to further analyze the scalar field's properties. This cumulant is a useful tool for characterizing the critical behavior of the scalar field. By examining the gauge field and scalar field correlations in the Lorenz gauge, this research contributes to a deeper understanding of quantum field theory and its applications in statistical physics. The relationships between gauge-dependent and gauge-invariant correlators are crucial for advancing our knowledge of quantum field theory and its applications. The authors introduce a gauge-invariant operator, gamma x, defined as the exponential of the lattice Coulomb potential in the Lorenz gauge. This operator is invariant under local gauge transformations and transforms as a charged operator under global U(1) transformations. The correlation function of gamma x, denoted as g gamma x, y, can be computed as the correlation function of zx in the Lorenz gauge. In the H phase, the charged excitations associated with gamma x condense, resulting in a non-zero correlation function in the large xy limit. Moreover, the correlations of gamma x converge to those of the Gauguin local operator E gamma x in the limit j right pointing arrow infinity, corresponding to the ICSI model. This identification allows them to conclude that the critical behavior of E gamma x in the ICSI model is the same as that of the scalar field correlations in the law model with Lorenz gauge fixing. The authors also summarize the finite size scaling (FSS) relations used in their numerical analysis. They consider simulations varying kappa at fixed j, with the basic FSS variable being x equals kappa kappa c, L caret 1, nu, where kappa c is the critical value, nu is the length scale critical exponent, and L is the lattice size. They discuss the scaling behavior of RG invariant quantities, such as ratios of correlation lengths and binder parameters, and the susceptibility chi-o, which is used to determine the scaling dimension of a local operator aux. The finite size scaling, FSS, approach is employed to elucidate the universal features of the multicritical, MH, transitions in the CPN-1 model. The authors first recall the expected behavior of cumulants Bk, which should exhibit FSS behavior with a universal scaling function Bk, x, that depends on the boundary conditions. They then discuss the critical behavior of the MH transitions, noting that if the critical behavior is the same as in the ICSI model, the exponent nu should be approximately 0.6717 and the correction to scaling exponent omega should be around 0.79. The third cumulant, which diverges with an exponent of 3, nu3, is highlighted for its importance in predicting the critical behavior of its correlations, particularly through the Lorenz gauge representation of the charged operator gamma x. The authors derive an expression for the exponent eta, which is related to the helicity modulus upsilon in the Villen XY model, and show that eta equals 1 in the ICSI model. This result is argued to extend to all MH transitions for any value of n. Numerical results from Monte Carlo simulations are presented to investigate the nature of the critical behavior along the MH transition line. Simulations for different values of n and j are performed using cubic lattices with C** operator boundary conditions, and estimates of the critical value kappa c and the exponent nu are obtained. These estimates of nu are consistent with the xy value, providing evidence of a universal ICSI behavior. The measurement of the binder cumulant of the bilinear operator Qx confirms that the SU-n symmetry is broken in both phases. The transitions along the MH line do not show significant crossover effects from the ICSI point, and the results are independent of the specific value of J adopted. The simulation methodology involves a combination of metropolis and microcanonical updates, along with the use of a conjugate gradient solver to determine the gauge transformation that satisfies the Lorenz condition. The authors present Monte Carlo simulation results for one-component and multi-component lattice Abelian-Higgs models, focusing on the critical behavior of gauge-invariant energy cumulants, non-local charged correlations, and local gauge correlations. The simulations estimate critical point values of renormalization-group, Rg, invariant quantities Rz, Ra, Uz, and Ua for different n values. Table I, demonstrating good agreement among estimates and supporting universality. The critical value of the coupling constant kappa c is calculated for different n and j values, equation 42, with data agreeing well with the expected behavior for j right pointing arrow infinity. The scaling relation, 37, is verified by plotting Ra versus X for different n and j values, figure 2, with excellent agreement providing further evidence for universality. The Rg invariant quantities at the critical point also exhibit good agreement among estimates. Analysis of gauge-invariant energy cumulants reveals behavior consistent with equation 40 for B3, figure 3. The scaling curve is universal, applying to all n values and the ICSI model at j equals infinity. Non-local charged correlations exhibit n-independent critical behavior, equivalent to that in the one-component law model along the CH line. Charged correlation scale is L2 minus eta z f chi, x, with eta z independent of n. Lorenz gauge susceptibility chi z scales with eta z equals minus 0.744, confirmed by plots of MC data, chi z, supporting scaling behavior. The finite size scaling relation Uz approximately equals Fu, Rz, between the binder parameter and Rz further confirms universality. Scaling curves for all n values are identical, figure 5, indicating n-independent critical behavior of the charged sector. Local gauge correlations are analyzed, estimating the gauge field exponent eta A by examining finite size scaling of Fx. Micro-nu correlations or the susceptibility chi-A in the Lorenz gauge. Results demonstrate critical behavior in gauge and charged correlations for any n, with eta A estimated to be consistent with the expected value of 1, derived from the correspondence between the small momentum correlation of Fx. Micro-nu in the ICSI model and the helicity modulus upsilon in the dual XY model. The findings provide strong evidence for universality of critical behavior in lattice Abelian-Higgs models, with critical MH transitions belonging to the same universality class for n is greater than or equal to 2. These results are also relevant to the ICSI model, characterizing critical behavior of the non-local operator E gamma x. The 3D law model, a noncompact abelian gauge field minimally coupled with an n-component scalar field, exhibits a rich phase diagram with 3 distinct phases. These phases display different properties of gauge correlations, confinement or deconfinement of charged excitations, and behavior under global SU, n, transformations. Figure 1 presents the phase diagram, which demonstrates the presence of a critical point. Figure 2 shows the scaling behavior of the correlation length xi with respect to the system size L and the deviation from the critical point kappa c, confirming the presence of a critical point. Figure 3 presents a scaling plot of B3 for n equals 1, n equals 2, and n equals 25, demonstrating the scaling behavior of the binder cumulant B3 with respect to the system size L and the deviation from the critical point kappa c. The analysis confirms that the MH line, CH line for n equals 1, is the same as in the ICSI model, and therefore, eta equals 1 in all cases. This result is supported by numerical analyses of chi-a for all values of n considered. Furthermore, eta equals 1 also holds along the CH line for n greater than n star operator, where the transition is controlled by the charged fixed point of the RG flow of the AHFT. The paper concludes that multi-component law models can undergo different types of transitions driven by the condensation of charged excitations, CH and MH transitions along the lines that separate the H phase from the C and M phases, respectively. These transitions are controlled by different charged fixed points of the RG flow with non-vanishing gauge coupling. Gauge correlations play an active, but different, role at these deconfinement transitions and cannot be described by effective LGW theories. The transitions along the CM and CH lines are related to the spontaneous breaking of the global SU, n, symmetry, while the MH line separates two ordered phases, both characterized by the condensation of a gauge-invariant bilinear of the scalar field. The MH transitions are driven by gauge modes that undergo a critical transition without a local gauge-invariant order parameter. The study highlights the importance of considering gauge correlations and the role of the gauge field in understanding the phase diagram of the law model. The results have implications for our understanding of topological phase transitions and the behavior of gauge fields in condensed matter systems. The topological Mott-Hubbard transitions in the n-component Abelian-Higgs model are analyzed, focusing on the deconfinement of charged excitations and their universality class. This lattice gauge theory exhibits both topological and conventional Mott-Hubbard transitions. The authors employ a combination of theoretical and numerical methods, including renormalization-group techniques, to study the system's behavior. For any n is greater than or equal to 2, the topological Mott-Hubbard transitions belong to the same universality class as the transitions along the Coulomb-Higgs line for n equals 1. This implies that the charged excitations associated with the operator gamma x, equivalent to the scalar field Zx in the Lorenz gauge, deconfine at the transition. The renormalization group dimension of gamma x is estimated to be y gamma approximately equals 0.132, indicating its relevance in the system. The critical behavior of gauge local correlations is also discussed, showing that the associated susceptibility exponent eta A satisfies eta equals 1, similar to the ICSI model. The ICSI model is dual to the XY model, but the critical behavior of the charged scalar correlations along the n equals 1 ch line is not related to that of the scalar correlations in the XY model obtained for kappa right pointing arrow infinity. Numerical results, illustrated in figures 4 and 5, demonstrate the convergence of data points towards a unique curve, supporting the concept of universality. Figure 4 shows the plot of chi-z, L2 eta z for eta z equals 0.74 versus ρ equals xi, L for different values of n and j. Figure 5 displays the binder parameter Us versus the ratio Rz equals xz, L in the Lorenz gauge, demonstrating convergence to a universal curve for n equals 25 with j equals 0.4, n equals 2, and n equals 1 with j equals 1. The research provides significant insights into the topological Mott-Hubbard transitions, deconfinement of charged excitations, and their universality class, as well as the critical behavior of gauge local correlations and the relevance of the operator gamma x in the system. The critical behavior of the lattice Abelian-Higgs law model is examined in the context of topological transitions and their universality. The model's phase diagram is influenced by the interplay between the gauge coupling, scalar self-interaction, and external magnetic field, exhibiting two distinct types of topological transitions: the Coulomb-Higgs (CH) and magnetic Higgs (MH) transitions. These transitions separate phases with confined charges from those with deconfined Higgs phases. The MH transitions are controlled by the charged IXI fixed point, while the CH transitions, occurring for n greater than n approximately equals 7, are governed by a different, n-dependent charged fixed point obtained in the Abelian-Higgs field theory, AHFT. Estimates of the corresponding n-dependent critical exponents are reported, including nu equals 0.802, 8, for n equals 25, and nu approximately equals 148, pi squared n, for large n, indicating that law models with n greater than n displayed two distinct charged critical behaviors along the MH and CH transition lines. A non-trivial multicritical behavior may occur if the MH and CH transitions remain continuous up to their intersection point. The addition of fermionic fields to the law model is suggested, which could lead to different topological universality classes. While massive fermions are expected to not alter the critical behaviors, massless fermions might result in new topological universality classes relevant to condensed matter systems. The study concludes by discussing the potential for topological charge transitions in 3D non-abelian gauge theories with scalar fields in diverse representations, although the identification of relevant gauge-invariant matter excitations in these cases is more complex due to the nonlinearity of the gauge conditions, requiring further investigation. The research paper presents a comprehensive analysis of 41 distinct neural network architectures, evaluating their performance on a range of tasks. The study employs a systematic approach, utilizing a combination of manual and automated methods to identify and categorize the architectures. The authors leverage a novel taxonomy, comprising 14 distinct dimensions, to characterize the neural networks and facilitate a nuanced comparison of their properties. The analysis reveals a significant correlation between the neural network architectures and their performance on specific tasks. Notably, the study identifies a subset of architectures that exhibit superior performance across multiple tasks, suggesting a potential for generalizability. The authors attribute this phenomenon to the presence of specific architectural features, including the use of residual connections and attention mechanisms. The research also explores the relationship between neural network complexity and performance, employing a range of metrics, including floating point operations per second, flops, and parameter count. The results indicate a nonlinear relationship between complexity and performance, with certain architectures exhibiting diminishing returns beyond a certain threshold. The study's findings have significant implications for the development of neural network architectures, highlighting the importance of careful design and evaluation. The authors emphasize the need for further research into the underlying mechanisms driving the observed correlations and propose several avenues for future investigation, including the exploration of novel architectural features and the development of more sophisticated evaluation metrics. Deconfined criticality challenges the conventional Landau-Ginzburg-Wilson paradigm for phase transitions, and this section reviews various models that exhibit this phenomenon. The authors examine the Ginzburg-Landau model, compact U1 gauge theories, multi-Higgs models, and other variants, which describe phenomena such as superconductivity, antiferromagnetism, and the physics of low-dimensional insulating materials. Renormalization-group flows are crucial for identifying the relevant degrees of freedom and their interactions at long distances, enabling the understanding of deconfined criticality. The Encolour-London model, which exhibits a deconfined critical point in the absence of an external magnetic field, is a key example. Numerical simulations and analytical techniques have extensively studied this model, revealing a critical point where the system undergoes a continuous phase transition from an antiferromagnetic to a valence bond solid phase. The connection between deconfined criticality and emergent symmetry is also explored. In certain multi-Higgs models, an approximate O(4) symmetry emerges spontaneously at a weakly first-order deconfined phase transition. This phenomenon has implications for understanding phase transitions in condensed matter systems. The interplay between matter and gauge fields is essential in determining the phase structure and critical behavior of these models. The authors emphasize the importance of deconfined criticality in understanding the behavior of these systems, particularly at the point where the transition between different phases becomes continuous. This section provides a comprehensive overview of the theoretical framework for understanding deconfined criticality in various physical systems. This research paper delves into the critical behavior and phase diagrams of three-dimensional lattice gauge models, drawing on numerous studies of compact and noncompact Abelian-Higgs models, multi-component models with different types of gauge symmetry breaking, deconfined quantum critical points, and four-dimensional oxygen mononitride models. Theoretical estimates of critical exponents in superfluid transitions are discussed, providing insight into the behavior of systems near optimal doping. The interplay between global and gauge symmetries in three-dimensional lattice multiflavor scalar chromodynamics is explored, including phase diagrams and Higgs phases. The renormalization-group theory, widely applied in various fields of physics, is emphasized for its role in understanding critical behavior. The importance of finite-size scaling and numerical simulation of statistical systems is highlighted, offering insights into the critical phenomena of isotropic systems. The paper concludes with a discussion on the phases of SU(2) gauge theory with multiple adjoint Higgs fields in 2+1 dimensions, and three-dimensional lattice SU(NC) gauge theories with multiflavor scalar fields in the adjoint representation. These studies are significant for understanding the behavior of gauge theories and their potential implications for condensed matter physics. The quantization of non-Abelian gauge theories is rooted in foundational works by Yang and Mills, Gribov, and Singer. Yang and Mills' 1967 paper introduced the Yang-Mills field, a crucial concept in gauge theory that laid the groundwork for subsequent research. Gribov's 1978 paper addressed the quantization of non-Abelian gauge theories, exploring the Gribov ambiguity, which arises when attempting to fix the gauge in non-Abelian theories. This ambiguity is a consequence of the non-trivial topology of the gauge orbit space, where the gauge freedom is not trivially removable. Singer's 1978 paper provided additional insights into the Gribov ambiguity, offering a deeper understanding of the mathematical structure underlying the ambiguity and its implications for gauge theory. The authors build upon these foundational works, recognizing the significance of the Gribov ambiguity in non-Abelian gauge theories. By acknowledging the contributions of these pioneers, the authors establish a solid foundation for their research, which tackles the complexities of quantizing non-Abelian gauge theories.